All right, guys, let's go on to 2.2. 2.2 is pretty much about asymptotes. That's the deal with 2.2. So we kind of did this example. If I take the limit as x approaches 0 of 1 over x squared, what happens if I graph this? If I put this in my calculator, 1 over x squared is a hyperbola. Looks like this. Now, if I take the limit as x approaches 0 from the left, what's happening is that my graph is going higher and higher and higher. It's actually going towards infinity. If I take the limit as x approaches infinity 0 from the right, it's actually also going higher, higher, and higher. It's also approaching infinity. Therefore, my limit is approaching infinity. Why? What's happening at 0 that is causing my graph to go up like that? What it is a vertical asymptote. And now we can actually define vertical asymptote. Oops, I don't want to do that part. Sorry, not in highlighter. There we go. So, a vertical asymptote. Please spell it with one S. The mathematical definition is the line x equals a is a vertical asymptote. I'm just going to abbreviate these, of a function f of x if either the limit as x approaches a from the right of f of x equals plus or minus infinity, or the limit as x approaches a from the left of f of x equals plus or minus infinity. Got it? So that is our definition of vertical asymptote. So, quick example. If we did the example, the limit as x approaches 2 of 1 over 2 minus x. And I'm going to say 2 minus x from the right. Got it? Now, multiple ways of doing this. One is you can graph it, and then you can see that at x equals 2, your graph tends to look like this. And you can tell that as it's coming from the right, it's going down towards negative infinity. The other way of doing this is substitution method. Plug in 2. Well, when I plug in 2, I get 1 over 0. We've had this conversation. You can't divide by 0, right? So what happens is if your denominator is getting small, your fraction is getting big. Well, if your denominator is getting really small, that means your fraction is getting really big to the point where it's going towards infinity. Now you got to figure out, though, if it's positive or negative infinity. Well, this is going from the right. So pick a number to the right of 2. 3. 2 minus 3 is negative 1. So that means these would all be negative. So that's why it would be negative infinity. Got it? So pretty much your shortcut to this is set the denominator equal to 0. So anytime your denominator equals 0, you're going to have a vertical asymptote. What if we look at this graph? And I want you guys to graph this on your calculator. X squared minus 1 over x squared plus 1. Now, when you graph this, please realize the numerator has to be in parentheses divided by the denominator in parentheses. And when you graph it, your calculator, your graph, should give you something that looks like this. This does not have a vertical asymptote, right? But what it does have is a horizontal asymptote. It's got a ceiling. This graph isn't going any higher than this ceiling. Now you can use your trace button, you can use your table function on your graph, whatever it is. But as I traced it and try to go bigger, like x equals 1, x equals 2, x equals 10, x equals 100. If I go to my table, try to plug in 100. You can plug in 100 in both of these. 100 squared minus 1 divided by 100 squared plus 1. What does it start equaling? You should hopefully realize that this is getting closer and closer to 1. What we actually did was took the limit as x approached infinity of fx. As in, if my x's get insanely large, I get a limit. As in, this graph isn't getting any higher than 1. So that means I've got a horizontal asymptote at 1. So let's do now the mathematical definition of horizontal asymptote. The line y equals b is a horizontal asymptote of the graph of f of x if, again, one of two things happen. The limit as x approaches infinity of the function equals b, or the limit as x approaches negative infinity of the function equals b. So anytime you're figuring out the limit as x approaches infinity, I'm really asking for the horizontal asymptote. Got it? So, for example, if I take the limit as x approaches infinity of 1 over x, if I do substitution, I get 1 over infinity. That makes no sense. But think of fractions. If my denominator gets really big, the actual fraction gets small, right? Like 1/4 of a pizza is smaller than 1/2 of a pizza. 1/8 of a pizza is smaller than 1/4 of a pizza, right? So as my denominator gets infinitely big, my fraction gets ridiculously small. It's actually getting closer to 0, so that means you have a horizontal asymptote at y equals 0. Well, if I graphed 1 over x, and hopefully you guys recognize 1 over x, you get this hyperbola, and that's the case. As my x gets closer to infinity, as my x's get bigger and bigger and bigger, this graph, this one has a floor. It's not getting past 0. It's going to get really, really close to 0, but never actually equal 0. Got it? Another example. What if we did the limit as x approaches infinity of sine of x? Well, that makes no sense. Sine of infinity, that doesn't help you. Let's try to remember what the sine graph looks like. Remember, the sine graph is our waves. It starts at 0, goes up, and then goes down. Choo, 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 choo. It's our waves. Now, as my x's get bigger, what's happening to my sine graph? It repeats. It's going from +1 to -1. It stays in between from -1 to +1. But it does equal -1 and +1. There is no horizontal asymptote here. So in this case, D and E does not exist. There is no horizontal asymptote. Not every graph has a horizontal asymptote. Got it? So you just kind of have to be careful about that. Now, time for the shortcut. There is a shortcut to this. Let's write it out. And these are only polynomial divided by polynomial. If the degrees of the numerator equals the denominator, then you're going to look at the coefficients. If the degree in the numerator is greater than the denominator, there is no horizontal asymptote. If the degree of the numerator is less than the denominator, then the horizontal asymptote is at y equals 0. So let's do an example. Remember, if at any point I am going too fast, you may stop the video, rewind, do whatever else you need to do. Okay, so let's do a couple examples. This is very, very straightforward. So let's say I'm going to take the limit as x approaches infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Here are two polynomials. What are the degrees of each polynomial? Remember, the degree is the exponent. What's the highest exponent? Well, they're both 2. So that means I have to look at the coefficient of these. Well, the coefficient is the big number in the front. That's 3/5. That means the horizontal asymptote is at 3/5. At y equals 3/5 specifically. And that's it. Super easy. If I asked you for this one, what's the limit as x approaches infinity of 5x over 6x cubed plus 2? Which degree is bigger? Well, this one has a degree of 1. Remember, if you don't see it, it's a degree of 1. This one has a 3. That means this one is bigger. The denominator is larger. If the denominator is larger, that means it's going to go to 0. That means your x-axis is your horizontal asymptote. If I do the limit as x approaches infinity of 8x cubed plus 4 over 2x plus 1, this degree is 3, this one is 1, this one is now the bigger one. The numerator is bigger, so it means if the numerator is getting bigger, the whole fraction is getting bigger, it's going towards infinity. There is no horizontal asymptote, so it does not exist, or goes to infinity. And there you go. That's your shortcut for this. All right, homework. This is assignment number 3. Page 76, 2.22 through 26, even, 55, 59, and 60.